Okay, let's work our way through this switches tutorial. The first exercise here is just fairly simple. They show us a bunch of voltmeters, so kind of take in the different circuits there, and they just want us to rank the voltmeter readings. So if you haven't already done your highlighting, pause and go do your highlighting, and then you can check it with mine when you come back. So I'll start on the low side of the battery, and I'll just kind of highlight everything there. And then moving to the high side. Okay. Now let's look at what we have so far. Usually I'll highlight the obvious stuff and then go back and look at the circuit a little more closely. In this particular case here, I have, well, let me look at case A first of all. Now I have a switch open here, so I know that actually I'm not going to be able to draw any current from the battery. And if I'm not drawing current from the battery, I don't have a closed loop here. I know that there's no potential drop over my resistors. So for this case A, I can just actually keep coloring in the red. So if those were light bulbs, those would not light up. And then as I look at my other cases, I notice that actually structurally, they're all exactly the same. I have an open switch. And the only thing that's different in any of these cases is the EMF of the battery. So that differs in magnitude. But in none of these cases will the resistors be dissipating. So what my voltmeter is going to measure in every single case is red to blue, right? It's just going to measure the potential difference of each of these batteries. So I know that in case D, it's going to measure 9 volts. The blue to red will be 9 volts in D. Case B, it'll measure 7 volts. Case C, it'll measure 3 volts. In case A, it'll measure 2 volts. So in every case, we're really just measuring the EMF of the battery. So these are cases where, you know, you have an open switch. Again, switches are there for a reason because you don't always want the lights on, right? So this would be a case of the lights off. Do we still have a potential difference? Yes, we do, even without that current there. That's what makes the switch work when you close it. Okay, adding a little bit of complexity here. Now we look again at where the voltmeter is installed. And if you haven't done your highlighting, again, pause and do your highlighting on your own. See if you can come to some conclusions. And then you can rejoin the video. I'll start here. Positive side of the battery. Right away, as I'm getting maybe a little bit better at this, right, I see that for this case B, I can go ahead and paint all the way down through that resistor. That branch has an open switch. That resistor there will not be dissipating. And here I might notice the same thing. I see that there's an open switch in series with the battery. So I can look at this now and see that, right, neither one of those is going to be dissipating. And then same thing in case D with the right-hand resistor. The resistor going through the middle of D there will be dissipating, and we'll see that in just a moment. So I'm going to just change my color here and paint in the low side of the battery in every case. Here I have an open switch in series with the battery, as I do in case C, so I know that neither of these resistors will be dissipating, so I can go ahead and paint those all the same potential. That just means there's no potential difference across those. Case B. Case C, and then I can paint in case D. So just quickly to evaluate what each of these circuits is doing, I think that's important, is say if these were light bulbs, might be easiest to think about maybe for the moment. This one would be bright right here in case B, that has a potential difference across it. And in case D, I also have a bulb with a potential difference across it right there, a resistor, right? So those resistors would be dissipating if they were bulbs. Those bulbs would glow, right? The rest of the ones would be out. Okay, so I want you to just fully understand the circuit. You should be able to answer the question, but also know what's happening everywhere in the circuit to get the most out of these exercises. So now we're just looking at voltmeter ranking. So I can go through and look at this. I have in case A, my voltmeter is going to measure from red to blue, which is going to be 3 volts, right? It'll measure the battery potential there. In case B, I'm measuring from red to blue battery potential, which is also 3 volts. In case C, I'm measuring red to blue, again, battery potential here. In case D, I'm measuring red to blue, and all the batteries are the same in this particular case. So here, all the readings are 3 volts is my correct answer. Okay, moving on. So now we have a couple switches, and this question is asking us about an ammeter reading. So notice that first, that it's asking us about ammeter, largest to smallest in the ammeter reading. And notice where the ammeter is, okay? It's up in series with the battery. So that is important. That's super important. Let's say this battery, let's call this battery E. Oops, let's call this battery E. Okay, and let's just say all the resistors are R in this case. Okay, so all the resistors are identical. We're told that here. And let's call each of those resistors R. And our battery's ideal and all that business. So if we are supposed to be looking at the ammeter reading, which really means we're looking at battery current, the relationship that I care about, or the, sort of what can clue me in here, is that my battery current is equal to my EMF divided by my equivalent resistance. So here I can just rank inversely with equivalent resistance. So this is a good exercise. You can go through and look at these switch configurations and figure out what is the equivalent resistance for each case. With both switches open, I see that what that does is it takes this resistor out, and the other 4 resistors are simply in series in that circuit. And that gives me an equivalent resistance. I'll just kind of keep a little table of my equivalent resistances here of 4R for the case of them all being open. Okay. Then now let's go to the case where S1 is open and S2 is closed. Now when I close S2, what that effectively does is it brings the potential to the same value, right? When you close the switch, it brings the potential on both sides of the switch to the same value. So if I have these 2 points at the same value of potential, that takes these resistors out, because now they have the same potential difference on either side. There's no potential difference across the resistors. They're not dissipating at all. So the battery doesn't experience those resistors. So in that case, we have S1 open, S2 closed, and S1 is open, so this resistor's out. So really I just have 2 resistors in series. That gives me an equivalent resistance of 2R. All right. Just going to kind of erase so we can start over here. My next case is S1 is closed here. So now I have this parallel set. That's important. S2 is open, so that keeps those other 2 above S2 in the running. So this parallel set here is going to have an equivalent resistance of R over 2. So that's basically going to be the 3R that are in series and the R over 2 that is in series with those, once you would collapse that. So that actually gives me like 3.5 R, or 7/2 if we're going to write this in terms of fractions. 7/2 R for that case. And then The very last case here is both switches are closed. So this one is closed. This one here is closed. So as S1 is closed, again, this makes that combination be equal to R over 2. When we close S2, it gets rid of any potential difference over these two resistors there. So it knocks those out. So that just gives me 3/2 R as my equivalent resistance. And then I would just rank inversely for current, because the greater equivalent resistance, and here we're using this relationship, the greater the equivalent resistance, the smaller the current I draw from the battery. And if we notice where the ammeter is, it's measuring battery current. It's wired in series with the battery. So that gives me D, B, C, and then A is my ranking there. So now we're looking at the same circuit here, but we are concerned with the voltmeter readings. Okay, largest to smallest in terms of voltmeter readings, and check out where that voltmeter is sitting. Kind of interesting spot there. It's sitting over switch 1. What that means is that whenever switch 1 is closed, that voltmeter is going to read 0, right? It's just like there's no component inside there, inside that switch. There's nothing to either dissipate energy or supply energy to the circuit. And that's what potential difference is about, right? It's about an energy change in the circuit. So there's nothing to do that when I close the switch, it's just a wire. So when S1 is closed, I know that both of those cases is going to, will measure 0. So let's see, I could have a table here for my voltmeter reading. So whenever S1 is closed, that's these two cases right here, I know that my voltmeter is going to measure 0. So the only two cases I really need to explore is S2 open and S2 closed there. So let's explore S2 open first. That's the case that's sitting right in front of us. And S1 open, right? So S1 open and S2 open. And when we have that, when S2 and S1 are both open, it takes this resistor out there. And then maybe use some highlighting to make really clear what this voltmeter is measuring. I'm going to use a couple different colors here. I'll use green on one side of the voltmeter. Like, what's this voltmeter even measuring? And then I'll use, say, purple on the other side of the voltmeter. I'm going to go purple all the way through the resistor that's wired in series with the voltmeter, because that resistor is not dissipating with S1 open. So we're looking at the open case right now, just to be super clear. Okay, so I can see then that what this voltmeter is measuring is purple to green, which is the same as the potential difference over this resistor right there. So essentially that voltmeter is measuring the potential difference over this resistor up here. So it's as if this voltmeter is wired right here. It's the same thing, right? So we have to be able to analyze circuits because they're not always going to appear visually in the most straightforward way. So the highlighting is really, really helpful for that. Well, great. What I have then with both the switches open is I just have 4 resistors in series. And so the drop over any one of those resistors is just going to be E over 4. So in this first case of open, E over 4 is what we'll measure on the voltmeter. Okay. Now what happens when we close? The only difference now here is that we close switch 2. When I close switch 2, it takes these out. And so my voltmeter is still measuring the drop over the second resistor here. But now I have only 2 resistors in series for my whole circuit. So now I'm going to measure E over 2, because the drop over each of the 2 in series is just going to be half of the battery potential. Okay, so now I have, not only can I rank my voltmeter readings, but I know exactly what the voltmeter is going to read in each case. So the greatest reading will be case B at E over 2, then case A at E over 4, and then cases C and D are equal to one another, and they will both read 0 in that case. Okay, so we're moving on in complexity here. We have now 3 switches. And I'll take you through some of this, but really, I mean, it's kind of the same thing over and over again. It's worth doing, though. Every time you work through something like this, it helps you be more familiar with what's going on in a circuit. In this case, we're asked to rank voltmeter readings. So notice where this voltmeter is sitting. It's sitting right next to the battery. Let's say this battery has some potential difference E, and all the resistors are identical resistors. Let's say they all have resistance R. So this voltmeter here is measuring the potential drop over a resistor that's sitting in series with the battery. Yeah. So really, what we can think about is that we are going inversely with the equivalent resistance for the whole circuit. So the current through this resistor, I'm just going to circle this resistor. That's a resistor that we're interested in. Its resistance is equal to R, right? Resistance isn't going to change. So if I look at V equal IR for that, the only thing that's going to change the potential drop over that resistor is changing the amount of current going through it. Now, it happens to be that for this resistor, it's in series with the battery, so that happens to be the battery current. Remember that battery current is equal to the EMF divided by the equivalent resistance. So in this case, we can rank inversely with equivalent resistance. So that's what we're going to do there. So this is good practice. You can go through these different switch configurations and figure out what the different equivalent resistances will be. So I could go through each of those and look at that. With all switches open, then basically that is going to take out, all switches open is going to take out this resistor and this one. So I just have 4 resistors in series there. My equivalent resistance is 4R. Then I close switch 3. So closing switch 3, this is case B here that I'm looking at. Switch 1 is open, 2 is open, 3 is closed. Closing switch 3 brings this resistor into play. So now this resistor is there. If I calculate the equivalent resistance for that case, I get 8/3 R. So you should be pretty good at this particular skill, calculating your equivalent resistances. So here you'll calculate equivalent resistance for every single one of those cases and then rank inversely with that. I will go through just to help you check your work as you're going through and write out what the equivalent resistances are. So the equivalent resistance for case A, as I had said, there was 4R. The equivalent resistance for case B is 8/3 R. The equivalent resistance for case C is 2R. Case D, 2R as well. Equivalent resistance for case E is 7/2 R. Equivalent resistance for case F is 13/6 R. And equivalent resistance for case G, 3/2, and case H, 3/2 R. Okay. So yeah, be sure that you can confirm all these values. And if you go through, that's a skill that you want to have really cold right now. Make sure that that's working for you. So if we rank inversely with those, the ranking that we're going to get here is that G is equal to H. That's going to be our largest drop over that first resistor because we'll have the most current. In other words, it'll draw the most current from the battery. Then C is equal to D, then F, then B, then E, then A.